So we talked a little bit about mass defect and binding energy and stuff like that last time, and why you get energy using Einstein's equation equals mc squared. Again, the essence of why mass and energy are interchangeable. That's a tough one, but that was one of the things that Einstein came up with in his theories of relativity, and that is really where the energy comes from when we're talking about nuclear reactions and nuclear energy. So, a nuclear reaction tends to occur when you have a nucleus that gets struck by another nucleus or another particle and then changes into something else. We call that a nuclear reaction. The technical term is a transmutation. Transmutations can occur naturally or they can occur artificially, in which case we call it artificial transmutation. Okay, but that's where a nucleus has changed, and usually in the process of changing, you're going to get some energy released. Sometimes you can get energy absorbed depending on what's going on. But this whole process was discovered by Ernest Rutherford, 1919. This guy was doing a lot in the world of the atom and the nucleus. Remember, he was the one that gave us, what else did he give us? The gold foil experiment, nuclear model of the atom. What he did is he bombarded nitrogen-14, okay, with alpha particles, and he found that protons came off. And he started with nitrogen-14, he started with alpha particles, which remember is the helium nucleus, and he was receiving these protons. So his big question is this: did he simply chip a piece off of the nucleus? Did he hit the nucleus and cause a proton to come flying off? Or did he actually create a new element by having that alpha particle being absorbed and creating some kind of a new element? That was his big question. And so in order to answer that question, he looked at what was going on and what was being created. And he thought of it kind of this way. I'll show you this picture here. Okay? Here is our nitrogen. Imagine our nitrogen nucleus is sitting here. And he thought about it as being two possibilities. He knew that he was getting a proton, okay, as one of his things that was flying off. But the question was, did the alpha particle just hit and go take a proton off and create a new element? Or did the alpha particle actually get absorbed and become part of the nitrogen nucleus, and then a proton and some other new element was given off? That was his question. So that was kind of what he looked at to see what was happening. So with additional research, what Rutherford found is that two particles did emerge. That two particles did emerge. That in fact the alpha particle appeared to have disappeared. It wasn't that he was just nicking the nucleus. It was actually being absorbed by the nucleus, and you're creating these two other new products. So he did this process called artificial transmutation, and it was actually like creating a new element. It was kind of cool. People kept doing research like this and seeing what they could do, and in the late 30s, Enrico Fermi, for which Fermilab is named after, that's the big particle accelerator outside of Chicago, he discovered that neutrons were a great thing to use to create artificial transmutation. So instead of using alpha particles, he'd bombard things with neutrons. Why would a neutron be better? Because there's neutral, so there's no electrostatic deflection or repulsion. They're not repelled electrostatically from the nucleus, so they can get in there and get close to the nucleus much more easily than a charged particle can. As soon as he figured this out, they started messing with things and they created new elements. That's when neptunium was created and plutonium was created, named after obviously Neptune and Pluto. Uranium, named after Uranus. Yeah. That's okay. So it's like, this is kind of like fun. We're in the lab, we're making new elements, life's cool. We can bombard things, we can transmute elements, we can make new stuff. And ultimately, we need to go back to this graph. What is this a graph of again?
Average binding energy.
Average binding energy per nucleon. That's the critical thing. Because really, as a nucleus gets bigger, it's going to have more binding energy because there's going to be more of a mass defect. But what you really want to know is the binding energy per nucleon. Again, the most stable nuclei are the ones that have the most binding energy per nucleon, which is iron. Your textbook actually says it's, I think, nickel, which is the next one up. But it's all right in that range right there. And just a reminder that, as if we were to go this direction, taking bigger nuclei and making them smaller, energy would be released, and that would be fission. And if we are going this direction, taking smaller nuclei and globbing them together to make bigger ones, energy would be released, and that would be nuclear fusion. Let's start with the idea of fission. Fission was discovered in the late 1930s, 1938 to be exact, and there was a couple of German scientists, Otto Hahn and Fritz Strassmann, and they discovered that they could take some uranium, and if they bombarded that uranium with neutrons, sometimes they would discover smaller nuclei that weren't there before and that were approximately half the size of the uranium nucleus. Now think about where and when this discovery is happening. Germany, late 1930s, okay? There's a lot of stuff going on in the world that's not so good, and to have these German scientists see this happen is a little bit scary, okay? Keep that in mind. It turns out that there were two German refugees, okay, German scientists that were refugees from Nazi Germany. They were living in Sweden at the time, Lise Meitner and Otto Frisch. And they were the ones that actually realized what these guys had done, that they had taken a uranium nucleus and fisted it, had broken it into pieces. I don't know if that's an actual word, but they had created nuclear fission artificially. They bombarded the uranium with neutrons and boom, made it break apart. This was a big deal. And these guys, you know, again, Nazi Germany was happening. We were moving into World War II, and there were some people that were not part of Nazi Germany that recognized that if the Germans had this technology, that was potentially a really dangerous thing. So let's look at what's going on here. Here's kind of a pictorial representation of what these guys discovered. You take uranium-235, pretty big nucleus. It's already relatively unstable. You bombard it with a neutron. Again, why do you use the neutron? It's neutral. It has more of a chance of getting into the nucleus than something that would be positively charged. What happens is the uranium absorbs that neutron and becomes uranium-236, which is excited, as you can see in the picture. Okay? And it's a very, very unstable nucleus. It actually only exists as uranium-236, I think, for a fraction of a second. But you can think of it this way, and this is one of the ways I read about it, is this big nucleus actually starts to kind of oscillate like jello, like wagga, wagga, wagga. And remember, the strong nuclear force is trying to hold it together, but the electromagnetic force is trying to rip it apart, right? And remember, the strong nuclear force is really, really short range. So when it's shaped like this end of the nucleus and this end of the nucleus have less strong nuclear force holding them together because they're so far apart from one another. And that electromagnetic repulsion can act greatly, you know what I mean, strongerly, right? And start to cause these ends to go apart. And that's the beginning of fission happening, okay? Because it starts to oscillate, and when it gets just the right farness apart, it just rips apart, okay? Now, see what's happening here? That's what I'm talking about. All right, okay? The critical thing with uranium fission is this. Other nuclei can be fissioned, whatever. They can break apart. But the critical thing about uranium is that when it fisses, and I have no idea if that's a word, but the important thing is that 3 neutrons are given off in the process. You now have two daughter products, which are about half the size of the uranium nucleus, and 3 neutrons. And why is that important? Because that's what we started the whole process with, was with a neutron. And if this one nucleus gives off a couple more, and there happens to be another one nearby, you can start creating what's called, someone said, a chain reaction. And that is what gives off lots of energy. If I take one uranium nucleus and break it apart, sure, it's a lot of energy for a nucleus, but it's no big deal. I mean, I could light a match and probably have more energy than that, okay? But if I can create one uranium nucleus breaking apart, causing other ones to break apart, causing other ones to break apart, all of a sudden I can get an incredible amount of energy. If I do it without controlling it, I've made a bomb, okay? If I do it and try to control it, I've got a nuclear reactor to produce energy, all right? Excellent. What makes the wagga, wagga, wagga? That's, you know, Elvis probably. Okay. Now, fission happens for uranium-235 much more easily than it does for uranium-238. Unfortunately, or fortunately, I guess, when you go out into, let's say, Utah and start digging around in the Moenkopi Formation to look for uranium, you're mostly going to find uranium-238. And when I say mostly, I mean mostly. Like 97, 98% of the uranium you find in the rock is uranium-238. Very stable nucleus, not much going on. You have to refine it. That's why we talk about refining for nuclear fuels. We enrich the nuclear fuels. We get more uranium-235 and less uranium-238. That's what you need to make a nuclear reaction. If the ground had a lot of uranium-235 in it, we'd probably just have random nuclear explosions happening all the time, which would be horrible. You'd be walking out in Utah enjoying the arches, and you'd be dead. It'd be horrible. Okay, doesn't happen. All right. All right. So here's if I was going to write down a nuclear equation for this. Here you go. I take a neutron, I add it to uranium-235. For a second, I get uranium-236. Again, it's very much a fraction of a second, and then. Again, there's a variety of things that can happen. This is a real common thing. Okay? I get these two byproducts, these two daughter products, and 3 neutrons. And again, it's those 3 neutrons that are given off that are critical. So same as we talked before, you guys, it turns out that if I was to look at the mass of this and compare it to the mass of this, there would be less mass in the end than when I started. Mass would have disappeared. Where did it go? Turned into energy, and particularly the kinetic energy of the molecules, which we know from our thermal unit that is also heat and thermal energy. Okay? The mass loss equals a large energy release. You get, for this particular reaction, you get about 200 mega electron volts per nucleus that has fissioned. Okay? Not very much. I mean, for a given nucleus, again, it's actually a very small amount of energy. You think if I took one uranium nucleus and blew it up in front of your face, you wouldn't think much about it. Be like, yeah, 200 mega electron volts, one little nucleus. However, if you have millions of nuclei doing it as a chain reaction, all of a sudden you have lots and lots and lots of energy. All right? So again, every uranium nucleus that breaks apart doesn't give off huge amount of energy. It does for that particular nucleus, but it's not a huge amount. But if we can create this chain reaction, because the neutrons are released, if those neutrons can interact with other uranium nuclei and create more fission and so on and so on and so on, it's kind of like an avalanche. Avalanche starts real small, one little thing, and if it triggers more and more things to release energy, boom, suddenly you have a ton of energy. Again, the reason this doesn't occur in nature most of the time is because most of the uranium in nature is uranium-238, which is relatively stable, and you also need what's called critical mass. You have to have enough uranium-235, and it has to be close enough to those neutrons that are being released so that those neutrons will interact with the nucleus. Okay? That's called critical mass. Then a couple would fission, they'd release some energy, they'd release some neutrons, and nothing else would happen. Okay? Yeah, it would just, not much going on. I don't know how much you need, but you need to have a critical density for it to happen. Another thing that's interesting is that the neutrons, in order to get a good reaction going, the neutrons that are released in that in a uranium-235 actually have too much energy. They're so energetic that they tend to go right by the nucleus without interacting with it. So you actually need to slow them down a little bit. And in nuclear reactors, we do that with what's called a moderator. I don't know how they deal with that in a nuclear bomb, though. So something can. Let's look at a picture. Look at that. Okay. Okay. Here it is. This is a nuclear chain reaction. Okay. Send in a neutron, hits this first nucleus, boom, blows it apart. You get these daughter products, which are green, but you get some more neutrons. They interact with more uranium. They break apart, and so on and so on and so on. So it becomes this exponential reaction. Every time it happens, energy is being released. If you do this uncontrollably, you get a massive explosion. Okay? If you can do it controllably, you can also, right, you can get lots of energy. And that's what a nuclear reactor is. A nuclear power plant or a nuclear reactor uses this process and tries to control it so that you can extract the energy and do work. That's one of the best things we know how to do it. Okay? Nuclear reactors were first invented in 1942, again by Enrico Fermi. This one he actually invented at the University of Chicago. The world's first nuclear reactor was built down in a laboratory basement at the University of Chicago in their physics building somewhere.
That doesn't make me.
Okay? It's still down there, I think. I think it's still there. And the basic idea, you guys, which is what we do to generate electricity, is we want to boil water. We like boiling water to turn turbines to make electricity. And so that's kind of the basic idea with a nuclear reactor. Use this nuclear energy to boil water to turn a turbine, which again is just a coil of wires in a magnetic field to generate electricity. It's pretty basic stuff, okay? nuclear energy is hugely concentrated. Hugely concentrated. 1 kilogram of uranium, which is about about the size of a baseball, holds enough energy to be the equivalent of over 30 freight cars of coal. Okay, so this is why nuclear energy is appealing, because it is immensely concentrated, and we love energy. We love power. We want it, and so the reason we pursue nuclear is because it is so highly concentrated. Pretty abundant. It still has to be enriched. You still you have to weed out that uranium-235, but yeah, it's out there certainly. Utah's got a ton of it. It would probably be sustainable for, well, sustainable is an interesting word. It would provide enough energy. The sustainability issue comes in with what we've been talking about, with the dangers of nuclear power and the nuclear waste. But in terms of pure quantities of energy, yeah, there's lots of it. Lots of it. Okay. Right now, we get about 1/5 of our energy here in the U.S. from nuclear power. But again, we're not big in the world on nuclear power. There's places in Europe that do a lot more. France, maybe Japan too. They've also come up with these other things called breeder reactors. I don't know how they work, but it's kind of cool. It takes the uranium-238, which is not really useful, and it turns it into plutonium, which is then can be fissioned, and you can get energy. 21%, that's about 1/5, right? So here's kind of what a nuclear reactor looks like. Here's a picture. I like pictures. Okay. Right. That's for fusion. You try to use those a little more. Yeah. So here's a basic nuclear fission power plant, energy power plant. Here's what you do. Okay. You got the core. The core has the fuel. That's the uranium and stuff. And then you got this thing called a moderator. Okay. The moderator is meant to slow the neutrons down so that they'll actually interact better with the next nucleus and do that. The control rods are different. These are the control rods. They're usually made of something like graphite, I believe. And the idea of the control rods is to control the reaction. Notice that they can be inserted or removed from the fuel where the reaction is taking place. The idea with control rods is it's made of a material that absorbs neutrons. If things get going too fast and it's getting too hot, stick the rods down in. They'll absorb some of those neutrons and slow the process down. If you need more energy, you need more heat, pull the rods out a little bit. More neutrons will interact with more uranium. You'll get more nuclear fusion, more energy being released. All this is happening in water surrounded by a huge amount of shielding that's meant to absorb the excess radiation and radioactivity, usually thick walls of concrete. This water gets really hot, starts to boil. Notice we put it in here, and then they do a heat exchanger over here so that this water, which is contaminated with radioactivity, doesn't mix with the water that's actually turning the turbine. We try to isolate the whole reactor segment. So the heat exchanger happens here. It boils another thing of water, which then goes to a turbine, which turns a turbine, which is a coil of wires and a magnetic field, generates electricity. You have a condenser to cool it back down, and voila, there it is. Pretty awesome stuff, pretty basic stuff. We're trying to boil water to make electricity. You can use nuclear power to boil that. You could use coal. You could use natural gas. You could use solar. But those are the ways we do it. This is how we do it with a nuclear one. Now, again, nuclear power in and of itself is not a horrible thing because we love power in this country and we love energy, and this is one really intensely concentrated source of energy. But it does have its downsides, as you all are well aware of. So let's talk about a few of the problems. One, you do have thermal pollution, just like Daniel was just talking about. You're going to have to cool that water down, and this is true with any power plant. You get thermal pollution from that. A major problem with nuclear is what do you do with the daughter products, the fission fragments. They tend to be radioactive, they tend to be pretty nasty, and they tend to last for millions of years. So what are you going to do with them? Right now, our current policy is to try to bury them, even though that's fraught with problems as well. Another issue is that the radioactive products interact with the structure of the reactor itself and make it brittle, right? So nuclear power plants tend to have a relatively short lifespan, on the order of 25 to 30 years, before they become so brittle by the intense radioactivity that they have issues. And like Chernobyl, you see what happens when you don't maintain a nuclear reactor very well. Okay? If those fission products somehow became airborne, it can cause serious health and environmental problems. Again, Chernobyl is a classic example of that. if you have a, what we call the China syndrome, the whole core melts down and explodes into the atmosphere, really, really bad. So that's a dangerous potential side effect. The China syndrome, and like I said earlier, these power plants tend to have a relatively short lifespan, about 30 years, because of the buildup of radioactivity and the structural weakening caused by the intense conditions. All right? So nuclear fission. So enough of fission. Let's talk about fusion. This is the ultimate goal in the world, okay? Because this is the way the universe works. Fusion is the process of bringing together smaller nuclei, or just neutrons and protons, to create nuclei, bringing them together to create something larger, and in the process releasing energy. This is how God has chosen to fuel the universe. Okay, I just recorded that. So just, no, but really, this is how stars work. Fusion is the fuel of stars, okay? Our sun does what's called the proton-proton cycle. It takes hydrogen nuclei, which is basically protons, takes 4 of those things, globs them together, creates a helium nucleus, and in the process releases 2 positrons, 2 electron neutrinos, some gamma rays, and some energy. Okay? It's a pretty sweet deal, because notice what we were talking about earlier, the byproduct is helium. Not only is it a noble gas, but it's fun. You can make balloons out of it, okay? It's not some sort of nasty radioactive material. You end up with helium, okay? Even bigger and heavier stars than our sun, they go farther than this this proton cycle. They go into what's called the carbon cycle. They fuse together even heavier elements. And when a really massive star dies, it creates this thing called a supernova explosion that is so intense energetically that it actually creates the heavier elements. So the heavy elements that you are made of and that create everything that we're around, those were created in a stellar explosion well before our solar system even formed. Fusion is a wonderful process. If we could somehow tap into it and do it in a controlled manner, we can do fusion, by the way. We know how to do this. We've done it uncontrollably, and it makes incredibly huge bombs. Okay? But if we could do it in a controlled manner, we would definitely change the world. If we could do it cheaply, well, not cheaply, efficiently and controlled, we would totally change the world. So there are people that are researching this. Can we get power from nuclear fusion? What are some of the benefits? Well, it releases more energy than fission does, nucleus for nucleus. You can use deuterium instead of hydrogen if you want to. This hydrogen and deuterium are readily available, as hydrogen being the most abundant element in the universe. And the byproduct is helium. Okay? Helium is created. It's a noble gas. It's inert. It's not radioactive. So you don't have to deal with the waste product. So pretty awesome possibilities. What are the issues? Okay? In order to get fusion to occur, you have to get nuclei to combine. Now, they don't want to combine. They're positively charged. They'd rather not be together. So they're going to be naturally repelled from one another. So in order to get them combined, you have to give them lots of energy, basically lots of heat. That's why we call the bombs thermonuclear devices, because it takes the thermo to get the nuclear going. So you have to give them enough kinetic energy that the nuclei will actually combine and touch. When you get something that hot, it's incredibly hard to control it. It's called a plasma. And it's incredibly hard to control for a couple of reasons. At the temperatures we're talking, most materials will melt. So you can't just build like a lead container to encase the plasma, because the plasma will melt the lead. The other thing is that something that high temperature comes into contact with something that's lower temperature, there's going to be heat dissipated, it's going to cool the plasma down. So it's really hard to confine a material. It's also really hard to keep something that dense. You need to have a high density and a high temperature so that there's a high probability of the nuclei that are moving around at such high speeds actually to combine. If you don't have things dense enough, they'll just fly around and not actually combine. Once you've created something that high temperature, think about the pressures involved. It's really hard to get something that high temperature. In a core of a star, no problem. Core of a star is already high temperature and high density, so it's just happening down in there. But here on Earth, it's hard to get hydrogen to that temperature and to that density to make fusion occur. There are people that are trying it, and Daniel keeps talking about the tokamak thing. One of the ways we're doing it, or trying to do it, is by using magnetic fields to contain the plasma using these magnetic fields. There's a lot of research going into how to do this. Dr. Octopus can do it all by himself, which is awesome. Currently, again, this is a technology that we can do, but we use it mostly in an uncontrolled environment, which we call a bomb, okay? A hydrogen bomb uses nuclear fusion. The first atomic bombs were not fusion bombs. They were fission bombs. It takes a fission bomb to ignite a fusion bomb, okay? The bombs that we drop on Hiroshima and Nagasaki, it takes an explosion that big to start the fusion process in a hydrogen bomb. So our original nuclear bombs that we used in World War II are now just the trigger mechanisms for the hydrogen bombs that we now have, to give you an idea of how big they are. So let's go back to 1938, 1940 and look at a little bit of history here, because it's kind of interesting. And if you guys are interested in this at all, I would encourage you to do some reading. There's a couple different books about this stuff that's really, really fascinating about what happened in World War II and nuclear. But in 1940, remember 1938 was when they discovered, in Germany, they discovered nuclear fusion. And I believe that, fission, thanks. I believe that they didn't actually know what they had done right away. Again, it took those other scientists in Sweden who realized what had happened. And they quickly went to the Americans and were like, you guys got to pay attention here, because if the Germans figure out what's happening, this is going to be bad. And actually, Einstein was one of the people that went to the president and said, listen, this is serious stuff. We better get on board here and try to figure out what's going on, because if the Germans develop this technology, they will win the war. It's going to be brutal. 1940, Hitler bans the sale of uranium from the Czech mines. Interesting. So he's suddenly trying to hoard his uranium. Okay. President Roosevelt authorized this thing called the Manhattan Project. It was based out of Los Alamos in New Mexico. And he gave J. Robert Oppenheimer control of the situation and said, you guys, see if you can do this. See if you can take nuclear fission and make a bomb. And we're going to watch a movie about this. It's pretty awesome stuff. It's really amazing kind of what came out of all that. We actually did develop a fission bomb. The first one was tested in New Mexico at a place called Trinity in July of 1945. At that point, we were in World War II. It was happening. We were fighting the war on two fronts, in Europe and in the Pacific. Soon thereafter, in August, so this is just 1 month later, we dropped a nuclear fission bomb using uranium on Hiroshima, okay? We dropped a plutonium bomb, I think, a day or two later on Nagasaki, okay? Lots of people died. These were incredibly successful bombs. And definitely they changed the course of the war at that point. There's a lot of history involved. I don't know what the right answer is, but there are some people that say it was probably a good thing that we dropped the bomb on them, because fewer people died than if we had gone head-to-head with Japan and tried to actually invade and take them over. I don't know the answer to that, but that is one argument. Recognize that we are the only nation that has ever used nuclear weapons, nuclear bombs on people. The Americans are the only ones that have ever done it, okay? Something to think about. Something to think about, okay? It is not incredibly difficult to make a nuclear bomb. What is difficult is extracting the uranium-235. Getting enough uranium-235 is the thing that is challenging. Yes? So obviously, since this time, tons and tons of bombs have been made. Very soon after this, people started thinking, well, hey, if we can make a bomb out of fission, we can probably make one out of fusion. And very quickly, the hydrogen bomb was made. We did the first hydrogen bomb. Very soon after, the Russians exploded one too, much quicker than we thought they were going to be able to. And the power that was released in a hydrogen bomb was astounding. We vaporized entire islands in the South Pacific, completely made them disappear by exploding a hydrogen bomb on them. Okay? We've done all sorts of testing. There was a ban, a nuclear test ban treaty back in 1963 that no longer could we test above ground. Throughout the 50s, we did all sorts of above ground testing, and usually in the South Pacific, because there's fewer people there and we can usually move them. But we actually had a testing facility in southern Nevada for a long time, and I think it's still active. I'm not positive about that. But yeah, but they weren't ever testing at Los Alamos. This place is actually the testing facility, which is in Nevada. We banned testing above ground because of fallout, but we started doing it underground. Here's a picture, okay? This is a picture of a nuclear explosion, and you can't see it very well, but this is This is 300ths of a second after the explosion. This is now 100th of a second later. Okay, so these are big bombs. This is 1500ths of a second later. This is top secret stuff. You can see the secret there in the picture. This is actually one of the first hydrogen bombs. This was taken from an airplane after the hydrogen bomb was detonated.